on today's show. Dallas is in California looking at earthquake science.
So this basically just acts as a fuse. If it's kind of overloaded, then this bit is gonna go, and therefore the bridge is gonna be saved.
That's the theory.
And I'm in Hawaii, witnessing the power of Mother Nature herself.
A magnitude 8.8 moment.
That's Bang Goes the Theory, revealing your world with a bang. Hello and welcome to Bang Goes the Theory. Now, the tragic events in Christchurch, New Zealand back in February were yet another reminder of how unpredictable and destructive planet Earth can be. But what can we do to limit the damage? Well, Dallas went out to California to find out.
The San Andreas Fault. It's the line where two of the Earth's tectonic plates meet and rub up against each other.
All the land over there is moving northwards at an eye-watering 55 millimeters per year on average, which means if I waited here for, I don't know, 15 million years or so, I'd see Los Angeles gently passing me by northwards to where Alaska is today.
Unfortunately, all this geological rubbing can result in major earthquakes. I spent a bit of time living in Los Angeles, and I often wondered if today was the day I was going to experience the earthquake everyone dreads, what they call the big one, a magnitude 7 on the famous Richter scale. In LA, people take this threat very seriously. This truck is designed to give people the experience of a major earthquake without it actually injuring them. I'll admit I'm a little nervous, so I've enlisted an earthquake expert to sit in with me and hold my hand.
Welcome to California, earthquake country.
Thank you very much.
How are you feeling?
Slightly sweaty palms, a bit nervous, not quite sure what to expect. I mean, what sort of number on the Richter scale would you have to be to actually sort of perceive an earthquake?
You could start feeling them at a magnitude 3, depending on what kind of rock you're on, how close you are to where the fault moved. You know, I think it would be good if you put on some of these safety glasses.
Oh, really? It's going to be that?
Well, you never can tell. Better to be safe. That's the idea.
Okay.
All right, we're ready.
So wow. Okay, so that's quite violent. My tea's almost.
Typical Southern California earthquake. Magnitude maybe 4.5 or so.
Wow.
Very much like what just happened here in the last few days. We had a 4.7 and 4.1. This is that experience if you were near the earthquake site.
So you actually had one of these, that sort of level recently?
Exactly.
There you go. Okay. Wow, okay, this is much bigger. Where are we now?
Around 7.5 now. This is where buildings collapse. This is where people get killed. This is the big one.
Okay, stop! Turn it off! Turn it off! Turn it off!
Well, that was alarming, but it does make Californians take earthquake resistance very seriously, particularly in the design and engineering of bridges that are the lifelines to major cities. Because when a big one really does hit, there'll be no reaching for the off button.
Somewhere that Californians know that only too well is here in San Francisco. Just over a century ago, the city was shaken to its foundations by a magnitude 8 earthquake that killed 3,000 people and left over 200,000 homeless. And then in 1989, it was hit by another massive earthquake.
At magnitude 6.9, it claimed 63 lives. And the city's Bay Bridge, little brother to the more famous Golden Gate Bridge, was one fatal location.
Believe it or not, but the bridge is actually built on wooden pilings, Douglas fir trees that are driven into the bay mud. And it's really hats off to the designers and the engineers that this bridge has lasted so long. But after 80 years, it's time to replace it. And currently, under construction, is a new Bay Bridge. And naturally, earthquake protection is at the forefront of its design.
To cope with the way that earthquakes can make the ground behave more like a liquid than a solid, the bridge has been built with very strong footings that splay out 100 meters deep into the mud below. It's just one feature that means this remarkable bridge will withstand that 7.5 magnitude earthquake and, more importantly, be able to stay open afterwards.
In the event of a big earthquake, what is it about the engineering of this bridge that's special?
Well, this bridge is built to what we call lifeline criteria. And basically what that means is that after a large-scale earthquake, this bridge will remain immediately available to emergency service vehicles like fire trucks, police, and then without having to do a complete rebuild, we'll be able to open it back up to public service.
This $5 billion bridge is being engineered to withstand a freak earthquake, the likes of which might only be seen once in 1,500 years. One way to do that is by building the bridge in sections, with a gap between them that allows for free movement.
Wow, this is amazing. So really we're at a junction point between two completely separate bridges here. Why can't you just have one long bridge? Why do you need these spaces at all?
If you don't have the bridge broken up into sections in an earthquake, it can potentially cause a lot of damage.
So if you can imagine we're in a big earthquake situation now, what would actually be going on here?
These two bridges are going to hit each other. The first thing that will happen is that sort of rubberized grommet there will take the first impact. And then this hinge pipe beam will allow the bridge to move in and out.
Almost a bit like doweling when you're putting your IKEA furniture together. That's sort of how they work as connectors.
Well, that's a fantastic analogy. That's exactly what they're doing. We don't want the bridges to skew or move sideways because you'll never get them back together. So the pipe beams keep the bridge together like this, and all of the energy will be transferred into what we call a fuse, this piece right here.
So this basically just acts as a fuse. If it's kind of overloaded, then this bit is gonna go, and therefore the bridge is gonna be saved.
That's the theory.
A similar device can be found up the bridge's one and only tower, which will support the road below.
So I'm 65 metres up in the very heart of the tower. It's actually not one tower, there's four completely independent legs, which are joined together by these connecting beams, which you might be able to see if you come down here. Now these beams, obviously, on a non-earthquake day like today, are going to give the whole bridge its strength, its rigidity, but they're also designed to bow and flex. And if the earthquake's bad enough, those beams can actually buckle. And the clever bit is that whole section can be removed and replaced with these bolts here. You can see how they just unscrew, and you can put a whole new section on.
Four legs are better than one in an earthquake, because if one breaks, the others will be strong enough to keep the bridge up. It's due to be completed in 2013, but to get an idea of what it's actually going to look like, I'm going to take a look from the very top.
How high are we going?
112 meters above the water.
112 metres above the water, so this is not for the faint-hearted. You're not faint-hearted.
No, I'm
He's
not.
all right, he's all right, good. If you get worried, if you get a bit nervous, then I'm here for you, okay?
All right, I appreciate that.
Well, I tell you what, you've got to have a head for heights for this. So just to take stock for a little bit, over that way towards San Francisco is the San Andreas fault, which is capable of serving up a sort of magnitude 8.1 earthquake. Over there towards Berkeley is the Hayward fault, which is capable of serving up a 7.1 magnitude earthquake. And I'm right in the middle. And it's a question of not if, but when. According to the US Geological Survey, there's a 70% chance of a big earthquake striking right here sometime in the next 20 years. But at least for the 280,000 people who drive across there every day, it's reassuring to know at least their bridge will be safe.
That is a beautiful build,
Really
isn't
is,
it? But what's happened to
really.
the old bridge now?
Very simple, being sold for scrap.
All right,
I mean, it's a
okay.
solid steel bridge. That is a lot of steel.
Are they just going to hold on to it while the price of scrap keeps going up?
I don't know. It's a good question. I'm not sure what is the price of steel at the moment.
I don't know, £150 a tonne? I mean, that is worth a lot of money, just scrap.
Exactly.
It did fare well for 80 years, though, that old
Yeah.
one, didn't it?
Yeah. Oh, no, it's amazing. It's a beautiful bridge, the Bay Bridge. Well, actually, when you say it's a beautiful bridge, that's part of the deal. It wasn't just we've got to put up a new bridge. The aesthetics of it, as you know, are vital.
They are vital, but for $6 billion, you expect a few
It
aesthetics.
wanted to look a little bit pretty.
Exactly,
Yeah.
exactly. Now, I've got a present for you, Jan. You may be wondering what this is. This is an actual bolt from the New Bay Bridge, because I was thinking about you when I was up there, thinking about you as an engineer and what you'd be thinking about this.
Missing...
The exciting thing about this bolt, not only is it a genuine bolt from the Bay Bridge, in honour of our visit from the BBC, they've put BBC, can you see that?
No way.
On every single bolt
What,
on the Bay Bridge.
BBC?
BBC, look at that.
British Broadcasting Corporation on all the boats.
On all, either that or the Bay Bridge Company. One of, not exactly sure, but
I thought that was a nice touch.
Thank you,
Nice
Dallas.
touch. That's
I
for
like
you
it.
to use wisely.
That is so nice. Did you bring me anything back?
Moving swiftly on. OK, now then, it is time for Dr. Yan.
Matt from Brighton sent in a really intriguing question. He asked, if a caterpillar has a scratch on it, will the butterfly have a scar after it's metamorphosed? Well, firstly, what is metamorphosis? Well, many insects have quite different looking stages to their life cycle. They often start out as a form that's specialised for feeding, and then they end up as something that's adapted for breeding. The change between these forms is called metamorphosis. Even things like grasshoppers metamorphose, but it's not so obvious because the babies look quite like the adults. It's a little bit more noticeable in things like dragonflies because their young are specialised for living in the water, whereas the adults, well, they fly around the place. Nevertheless, in both cases, the changes happen step by step, and that's called incomplete metamorphosis. But insects like beetles, flies, bees and butterflies do something much more extraordinary. And that's called complete metamorphosis. So the eggs hatch out as larvae, which feed voraciously. So think of maggots or those caterpillars on your vegetable patch. Those then seal themselves up as a pupa, which looks a bit like this. Then they emerge completely transformed as the sexually mature adult, like this butterfly. So in fact, this insect has been through 4 major stages in its life cycle: egg, larva, pupa, and finally butterfly. And although we call this insect a butterfly, actually it spent much more of its life as a caterpillar. It's just that this short stage as a beautiful flying and mating machine is so much more visible to us. So, back to the question, what if there's a scratch on the caterpillar? Well, to answer that, we need to look more carefully at the caterpillar's life cycle. Insects have a tough outer skin, so as the caterpillar grows, it needs to repeatedly shed this outer layer and grow a bigger one. Now, the hungry caterpillar doesn't really stop eating, so it has to actually molt and regrow skin 4 or 5 times. That means if a caterpillar suffers a scratch on the very outermost bit of skin, then it'll get rid of it by molting, and so the brand new skin won't have a scratch, and the adult, the butterfly, won't be affected at all. But what if the scratch went deeper, say into the muscle? Well, that's where complete metamorphosis comes in. I've set up a camera at London Zoo to capture a few caterpillars going through their pupal stage, but don't worry, I didn't harm them. Once the caterpillar is finishing its final molt, it attaches itself safely onto a branch and grows a special outer skin, a rigid case that looks nothing like a caterpillar. This is the pupal stage, and inside there it undergoes its final transformation into a butterfly. Now, I'm going to demonstrate with this jelly caterpillar I've made. Once it's in the pupa, the caterpillar secretes digestive enzymes and basically just kind of liquefies itself. The cells of what was once the caterpillar just die and disintegrate and break down. It's a process called apoptosis. It's kind of like melting the jelly. Now, even when it liquefies, a few vital structures do remain, and I've represented those here by sweets, and those include the central nervous system, the gut, and the thin innermost layer of skin cells. But most importantly of all, it also includes what are called the imaginal cells. Now, they're arranged down the body of the caterpillar here in a series of discs, and there they just remain, not doing very much, until, that is, it comes to just before the pupal stage. Then they spring into action. And using this mush for nutrients, they grow and multiply, developing into entirely new structures. So, for example, by the end of the pupal stage, the imaginal discs that were once in the legs of the caterpillar have now developed into the legs of the butterfly, and so on. And eventually, you end up, well, with something like this. Actually, it happens a bit more like this. Now, depending on the species, this pupal stage can last anything from a few weeks to 10 years. But eventually, a butterfly emerges, attractive and ready to mate, fulfilling its reproductive function. So, Matt, most damage to a caterpillar won't carry through to the butterfly stage because, amazingly, most cells just get completely mushed up and their contents reused. But if the caterpillar damages those few vital structures that survive through the pupal stage, then they can remain damaged in the butterfly. So for example, if it damages that thin innermost skin layer, then the butterfly might have scar tissue. And if the imaginal discs are damaged or even removed, then it's conceivable that the butterfly might not even develop certain structures. And that's actually how scientists figured out how this incredible metamorphosis works.
Thank you for that, Jan. Here's another little Janism, which I think you might like, being an aeronautical engineer that you are. Okay, so what I want you to do is imagine there you've got airport A, okay? And down here you've got airport B. Right,
Yep.
Now, here is my aeroplane. Now, let's imagine there's absolutely no wind and the aeroplane is going at a constant speed. Now, it takes off from airport A, goes to B and back again, so a round trip like that. Okay, so just imagine that journey.
Okay.
Hold it in your mind. Now, this time it does exactly the same journey, but this time there is a wind blowing from A to B. But the plane does the same journey, goes at the same speed relative to the air. Okay, so A with the wind to B, and then back against the wind to A. My question for you, which of those journeys is going to take longer, or are they going to be the same? I think this is really tricky. It sounds like it should be easy. Have a little think about this at home.
I like this. I mean, because an aircraft's engine power only dictates the speed it can go relative to the wind. So if it keeps the same power on the whole time, obviously with the wind blowing, it's going to go faster this way and
slower
that way. This one is a really good test of either logical deduction or algebra.
Yeah, I tell you what, have a little go at this at home. Get a pen and paper and actually sit down and see if you can work it out. It's tricky. Okay, Liz.
Thank you, Campbell. Now, back in January, I got the chance to visit Hawaii to check out the awesome observatories at the top of Mauna Kea. Hawaii is an absolutely stunning place, and the whole island chain literally erupted out of the ocean as a result of volcanic activity. So, I also grabbed the chance to get up close and personal with the might of Mother Nature herself. There's incredible heat coming off of this, lots of water vapor and lots of sulfur dioxide. You can really smell it and it hits your eyes. On the southern coast of Hawaii's Big Island, the volcano Kilauea constantly spews its lava into the Pacific Ocean. It's the most active volcano in the world. Since 1953, it's erupted 33 times and it's been non-stop for the last 18 years. It's so hot right here. Streams of 1,000 degrees Celsius lava pouring into the sea. This is Kilauea in all her glory. The lava from this volcano isn't the only threat here. Along the coast of the island, unstable volcanic rock can crash into the ocean, causing another destructive force of nature, the tsunami. Small tsunamis like those caused by landslides happen at least twice a year across the globe. But much larger ones can occur every 15 years or so, and they are caused by huge earthquakes at the bottom of the sea. Now, ordinary waves like these are created by the wind, and even though they look fairly tame today, they've still definitely got the power to knock me over. But add something like an earthquake, and you're talking about a wave with a different kind of power altogether. Woo! So how exactly are tsunamis different from ordinary waves? Surprisingly, it's not about their size, it's how fast and how far apart they are. Here's an ordinary wave. Now, the distance between each crest, or the wavelength, is usually about 100 to 200 meters. When an earthquake occurs, the sea floor is deformed. That displaces the body of water above it. And as this body of water attempts to regain equilibrium, you get your tsunami wave. The distance between each crest increases to anything up to 300 miles. Out in the deep ocean, a tsunami wave is only a meter or so high, but it can travel up to 600 miles an hour. It can hit land peak first or trough first, which looks like a sudden low tide. But crucially, as the wave approaches the shore and the water depth decreases, the speed of the wave also decreases. But that energy has to go somewhere. So instead, the height of the wave begins to increase. To 30 meters or more, the wave moves inland, anything up to 1 or 2 miles, and takes everything with it in its path. And sometimes the second wave, which can be anything up to 2 hours away, can be even more powerful than the first. Hawaii has been hit by at least 50 tsunamis since records began, and after 159 people were killed in 1946, the islands established their own tsunami warning center. It's one of just 3 in the entire world. And after the tragic tsunami of Boxing Day 2004, it took on a truly international role.
So these are seismometers all over the Earth. And up here on the screen above, this is seismometers that have actually seen something. Right now, we just have one white dot here in Southern California. If there were a big earthquake, we would suddenly see a whole bunch of white dots. And then as the energy spreads out across the Earth, you would see all of these dots would light up.
So you've got a 7.8 on the Richter scale. What happens next here?
My pager goes off. So I come running in here and I go and look at this screen over here.
Oh, wow, okay.
Each of these traces would suddenly show something, and basically the screen would go black. And we have to tell people when the tsunami is going to arrive.
How do you calculate that? Does the computer do it for you?
We know where the earthquake is, so we come over here. We know how fast the tsunami travels, because that depends only on water depth, so we can compute how fast the tsunami is going to travel and when it's going to arrive at various places. So the tsunami is going to be in 1 hour, 2 hours, 3 hours.
And there's Hawaii.
And it's going to take 15 hours to get to Hawaii.
These predictions are aided by pressure sensors throughout the Pacific, which allow the precise course of a tsunami to be tracked. 38 buoys dotted across the ocean pick up signals from sensors on the seabed and relay them back by satellite to the center in Hawaii. And once they've adjusted their predictions, the center issues warnings, not just to Hawaiians, but to people at risk all over the world.
Literally magnitude 8.8 moment.
With every tsunami detected, whatever the size, Gerard collects new data which he hopes will make their predictions even more accurate the next time a very big tsunami hits.
The size of the 2004 earthquake, that's a magnitude 9.2 or 9.3 earthquake, a real monster.
Yeah.
The chances of that happening again are very good. I mean, in all probability, it will be in the Pacific for the simple reason that the Pacific has most earthquakes, period.
Yeah.
For the Pacific, the 2004 tsunami was actually a godsend because it reminded us of the hazard, and we realized we're not ready.
Okay.
And so there was an immediate scramble, and the system was greatly improved, and we've got to the point now where we think we're ready.
Liz, what I'd love to know is, when you were out there in that boat, did the sea actually feel hot?
Oh yeah, we all leant over the side of the boat, dipped our hands in. It was like a hot bath. Really nice, except that we were so close. The fumes were something else. They were stinging our eyes, and we were inhaling some of it, so we kind of got out of there sharpish, to be honest.
It did look a bit close.
Yeah, it was. We were so lucky, though, because Kilauea hadn't actually been flowing into the sea for about 6 months or more. So we thought, right, we've only got one day to film this, we're never going to get it. 5 a.m. that morning, we get the call saying, you are the luckiest people alive. It's flowing for the first time in ages. Get yourselves on a boat and get some shots.
Fantastic shots. What I didn't really understand was the level of infrastructure behind that early warning system, particularly that bit of Hawaii. I didn't realise it was in charge of looking out for so much of the planet.
Yeah.
And you've got your man Gerard there with his pager. He's our primary source of contact.
He is. I think he's got a backup to the pager and a backup to the backup, though, and lots of other people working in the centre. But it's a fantastic place.
And presumably that's only going to get better.
Absolutely, yeah. OK, that's it for this week. We'll see you soon. Say goodbye, boys.
See you soon. Bye.
Bye.